today. Today we will start our discussion about transport layer protocols, and there are actually two dominant protocols, UDP and TCP. So, we will take them up one by one, UDP in this lecture and TCP in the next one. So, this is UDP, it actually stands for User Datagram Protocol. Okay. So, this is a transport layer protocol and this has got the following responsibilities. First of all, it creates a process to process communication path. Okay. So, till now we have talked about the network layer, and the network layer, the job of the network layer is to connect a distant machine to another distant machine. So, it is a machine to machine communication, whereas now we are talking about process to process communication. So, in this particular machine, in the source machine, maybe some process is running, some application process which is trying to connect to this other distant machine for some job. So, this process has to connect to the corresponding process there, that may be a particular application server on one side and that application client on the other side, whatever that application may be. So, this is a process to process communication path. And then this also has to provide control mechanisms at the transport level, and of course, this control mechanism in the case of UDP is very minimal, as we will presently see. So, this is a connectionless. Now, this UDP is a connectionless unreliable transport protocol. Okay. Now, of course, immediately the question would come in your mind is that why would we try to have an unreliable protocol, a protocol which is unreliable. Well, this is not unreliable per se. The point is it does not do anything extra for reliability, making it a very lightweight protocol. So, this is so this overhead, its cost is very low. So, in many cases that may be a very reasonable thing to have, where you do not expect a lot of errors, or you do not really care if some error occurs from time to time. So, in such cases you may use UDP. So, this is a connectionless protocol, more about that later. It only adds process to process communication to IP, performs very limited error checking as we have mentioned, and very simple protocol, has minimal overhead. This is the main point, it has got very minimal overhead. So, just to reiterate that point, say in this internet, say when you are talking about the IP protocol, you are talking about the connection from one machine to the other, all right. But whereas in this particular machine, a number of application programs may be running, so a number of processes may be running, and this UDP protocol connects one process to another process. So does of course TCP. So, that is the job of the transport layer, that is to make some connection available, some virtual connection available, although the UDP is a connectionless protocol, but anyway some virtual communication channel available to the corresponding processes. So, to summarize, IP is responsible for host to host communication. So, message still needs to be handed to the correct process, and UDP is responsible for delivery of the message to the appropriate process. Okay. Now, actually not only you have to understand that there is some kind of multiplexing and demultiplexing going on over here. In the same server, a number of processes may be running, and out of all those many processes, a good number of them may be using the same UDP protocol. Okay. Now, when well, sending out is all right, but when receiving a packet, the UDP protocol has to determine that to which process it will go to. That is one of its jobs, and the other of course is to make connections possible. There is a point over here, and this is a common task between both the TCP and the UDP, which is that you would see that till now we have been talking about communication through packets. So, our network, computer network is mostly a packet switched network, whereas so far as applications are concerned, mostly in most of the cases they do not really bother about packets. Okay, they may produce a chunk of data to be communicated to the other side. They may even produce a stream of data to be communicated to the other side. So, it does not work with packets. So, somebody has to take this stream of data from the application layer in general and chop them into small packets, and that is a job of the transport layer. So, both TCP and UDP does that. So, UDP is a transport layer protocol within the TCP IP protocol suite. It is simpler than TCP. UDP is simpler than TCP. So, TCP has higher overhead, has got more is more reliable. UDP is less reliable. Its reliability, if you want to have reliability and still want to use UDP, you have to take care of reliability in some other layer, maybe application layer or something. UDP lies between the application layer and the IP layer, and like TCP serves as the intermediary between the application programs and the network operation. So, if this is your IP datagram, the IP datagram would have an IP header, and the payload for the IP would be the entire thing, the UDP datagram, and the UDP datagram would have the UDP data which it derives from the application and the UDP header. There is a point over here which is when a particular application wants to communicate to another application, that is, or when a process is trying to communicate to another process which is in a remote machine. In that case, maybe it will want to talk to some particular machine, and up to now whatever we have seen, a particular machine means a particular IP address. Now, this IP address is handled by the IP layer, that means that the network layer on both the machines. But then how does the network layer get this IP address? As such, it is supposed to get the IP address, say destination source and destination IP address from the top, but there is a transport layer between the IP layer and the application layer, if you remember. If I sort of forget about we are talking mostly about the TCP IP protocol stack. So, talking about OSI protocol stack, we are not considering the session and presentation layer for our purpose for the time being. Anyway, the destination IP address is known to the application, but it has to be communicated to the network layer, and of course, transport layer has got nothing to do with the IP addresses. So, there is a little bit of sort of backhand deal over here, which is that application layer does communicate the source and destination IP layer IP addresses to the transport layer, and the transport layer passes it on to the network layer, does not do anything with it except maybe considering it for the checksum, which we will come to that later on. So, this is known as IP pseudo header, because this is not a real header for the UDP protocol or TCP for that matter. So, this IP pseudo header contains the 32-bit source IP address, 32-bit destination IP address, and then these other 16-bit UDP length, etc. So, this is the header which is passed on to the IP layer, and the so this has got, so this is in the same stack, that means it is in the same stack in the same machine, all right. But then if you remember that these headers are actually, or usually they are meant for communication between peers, that means the transport layer, let us say the UDP on this machine and the UDP on that machine, they will communicate via this UDP header, all right. So, that is the proper header, and the pseudo header, it just takes that information about IP addresses, etc. from above and passes it below. So, what does the real UDP header, the one that it uses to communicate with its peer on the other machine, it contains a 16-bit source port number, 16-bit destination port number. Remember, these were 32-bit source IP address, and these are 32-bit destination IP address, assuming IPv4 of course. And there is something else over here called a port number. We will come to this later on. 16-bit source port number, 16-bit destination port number, 16-bit UDP length, 16-bit UDP checksum, this may be optional, and data if any, possible odd bytes, and a pad. So, that is the length of the header and the data. So, we have got this source, destination, total length and checksum. Let us go through these one by one. Source port number 16 bits, ranges from 0 to say 65,000. Port number used by the process running on the source host. Actually, if you think about that multiplexing and demultiplexing that I was talking about, that in the same machine number of processes may be communicating, and out of all these number of processes, a good number of them may be using the same protocol, namely transport protocol, namely UDP, and while the others are using maybe the once again the same transport protocol, namely TCP. Now, when a particular packet comes, suppose of course you can see that whether it is a TCP packet and UDP packet, you can make that out, but once you make it out, after that you have to decide that out of all the processes using UDP, for which process is this packet meant. For this, all these different processes are associated with a different port number, and looking at the port number, the UDP may decide that okay, it is supposed to go there and supposed to go there. That is the demultiplexing part. Multiplexing part, of course, it has to come with a source port number, it comes. So, there is a source port number and a destination port number. These are used by UDP for multiplexing and demultiplexing at its own level. And this is a number which is 16 bit long. So, 16 bits will give you from 0 to 65,000. So, these are the so called port numbers, and port number used by process by the process running on the source port. Now, how is this port number, I mean initially from where do you get this port number, etc. We will come to that in detail later on. So, similarly there is a destination port number. So, once again 16 bits, port number used by the process running on the destination host. In most cases this is a this may be a well known port number. I will tell you what a well known port number is. Then length, this is 16 bits. So, defines the total length of the user datagram header plus data. So, note that means maximum size of data is 65k kilobytes, that means 20 bytes for IP header and 8 bytes for UDP header, of course, you have to subtract. So, that is the overhead. So, that would be the maximum size of the packet that they can handle. And finally, a checksum. So, used to detect errors over the entire user datagram. Okay. So, this is a checksum, 16 bit checksum, and this includes 3 sections. One is the pseudo header. This is part of the header of the IP packet. It ensures that if the IP header is corrupted, that the user datagram is not delivered to the wrong host. That means since the pseudo header contains the destination IP address, even if the IP header is somehow corrupted, this does not get delivered to the wrong place. So, the pseudo header is there, the UDP header is there, the one that we just discussed, and the data. So, all these 3 taken together forms the payload for the next layer, that is the IP layer, and the checksum is computed over this entire body, and that is so it also carries. So, there is some amount of error checking and error detection that is done. Right now we are talking about UDP. So, it is done by UDP, and that is the extent to which it will go for providing reliability. Beyond this, if the entire packet is lost somewhere, the UDP cannot do anything about it. So, these are the 4 fields of the header: source port number, destination port number, total length, and checksum. And regarding the UDP operation, this is a connectionless service. This has very minimal flow and error control as given by the checksum. It does the encapsulation and decapsulation, forming of packets, it uses some queuing, and does the multiplexing and demultiplexing. So, let us look at these operations one by one. This is a connectionless service. That means each user datagram sent is an independent datagram, all right. Which means that suppose some particular application has sent one UDP and is going to send another one. Now, these the I mean layers below this application, they may be coming from the same source application process, destined for the same destination application process. So these two datagrams, but they are going to be treated independently by the rest of the network layers and hence the network. Now this means a number of things. First of all, it may so happen that one of these two packets may go in two different directions, may be routed differently, okay, because there is no connection. This is a completely datagram oriented service, connectionless service. So the two datagrams may travel different paths. Secondly, one of them may get lost, of course. Thirdly, what might happen is that they may go out of order, okay. The datagram which was sent earlier may go there later on, and so on. And the point is that for all these mishaps, UDP is not going to take any responsibility. It is taken for granted that whatever application is using this UDP is resilient to such things happening. So there is no relationship between different user datagrams, and the user datagrams are not numbered, meaning that when the datagram which was sent later, if it arrives earlier and vice versa, there is no way of knowing, unless of course in the application layer itself you have taken some care to identify that. So it is a connection. So no connection establishment, since there is a completely a connectionless service. So there is no question of any connection establishment, and since there is no connection establishment, there is no connection termination either. Each user datagram can travel on a different path, this we have already mentioned, and only processes sending short messages should use UDP. All right. Actually, we will discuss more about the uses of UDP later on, but the point is usually UDP is used by those in those cases where you send one packet and that is the end of it. All right. You do not, I mean, when you are trying to send a stream of packets or a stream of bytes, etc., usually you would not use UDP, when a large stream of bytes, that is. So this is a connectionless service. So far as flow and error control is concerned, that is that may be another job of the transport layer, but as I already mentioned that UDP does very little. It is very simple and it is unreliable transport protocol. There is no flow control. The receiver may overflow with incoming messages. So no error control except for the checksum. Now what happens is that suppose a receiver is getting a large number of UDP packets. If it wants to just say stop or slow down to the senders, it cannot do it, okay. So if, and of course if it overflows, some of the packets would get lost, and then there is no error control except for the checksum. So sender does not know if a message has been lost or it has been duplicated. An error in the checksum causes an user datagram to be silently discarded. So this is very simple. Of course, being very simple also means that this is very efficient, this has got very low overhead and things like that. It does encapsulation and decapsulation. So which is of course a fundamental job of any protocol in the transport layer. I mentioned that it has to form the packets. So this is where the packets get formed from the streams of data which is supplied by the application layer. So this is going to get it, chop it into a piece, put its own header, pseudo header, etc., and then pass it down. So to send a message from one process to another, the UDP protocol encapsulates and decapsulates the messages. So this is just a standard way as it goes down the stack, message from the process. So this is the UDP data, it adds the UDP header, then of course IP header, frame header, etc., and it is decapsulated in a similar fashion. Now about queuing. So each port has an associated incoming queue or incoming and outgoing queue, depending on which way the communication is taking place. So you see a port is not just a number. Along with a particular number, there will, I mean, inside the OS there will be a queue of data being communicated in the machine. So, there will be an incoming queue and there may be an outgoing queue. For the outgoing queue, what UDP does is UDP removes message from the queue one by one, adds the UDP header and delivers them to IP. For incoming queue, UDP checks to see if an incoming queue exists. That is the first thing it will do. It will check whether the incoming queue exists. If there is no, if there is, UDP sends the user datagram to the end of the queue. And who is going to consume from this incoming queue? Naturally, the particular application process. A particular application process or whatever it is who is serving. So, he will consume from this queue which is being fed from the UDP for the, so far as the incoming queue is concerned. So far as outgoing queue is concerned, the application process is going to put things in the queue and the UDP will take out the message to be communicated from the queue. If there is no incoming, if there is no such port, UDP discards the user datagram and asks ICMP to send a port unreachable message. Okay. So if there is no port, so which this means that a particular packet has come meant for a particular port and that port does not exist on this machine. So, it will send an error message. We will come to the details of ICMP messages later on, but it will come to the it will send an error message saying that the port is unreachable. And if you remember, sometimes this particular feature is also used to get in order to generate this ICMP message, sometimes a packet is sent to a improbable port number. So, that ICMP message is when you get back, you know that you have reached the destination, but of course, there is no application over there. We will talk about in more detail about ICMP later on. And lastly, as I said, it does multiplexing and demultiplexing. Several processes may want to use the services of UDP. UDP multiplexes and demultiplexes to handle this. Now, use of UDP. This is suitable for processes that require simple request response communication. As I said that suppose there is a simple request which may be sent by UDP, and then to this request there is just one message as a response. So, that may also be sent back as an UDP. So, and especially this also depends on the kind of network you have. Suppose you are communicating only inside the LAN. In that case, you may not like to have an overhead, you know that this is not going over the WAN. So, this is going to be is expected to be much more reliable. In that case, you may not like to incur any extra cost of providing reliability, etc., because you know that the underlying network is quite reliable. And if the secondly, if your process is such that there is a simple message coming and there is a simple response, in that case a simple UDP protocol may be sufficient. This may also be suitable for processes which include internal flow and error control mechanism. That means, if the application process itself is handling some flow and error control, if the application, that means it is being handled at an upper layer, then you do not want to duplicate it in the transport layer, in which case you would use a simple protocol like UDP, so that it is more efficient because the reliability is being handled by somebody else anyway. So, that is another case where UDP is a very suitable protocol, and this may also be suitable for multicasting and broadcasting. Going to some specific examples, This is used for management processes such as SNMP. Okay. We will talk in more details about SNMP later on, but SNMP is a simple network management protocol which is used for managing network. Now, for managing network, what happens is that we have this central network management software which from time to time may probe different network boxes to see if their health is all right, or to collect all kinds of statistics and things like that. So, this is a simple message response kind of system. So, it sends a message, that means it asks for a query, it queries a particular managed device in the network, that device responds with some statistics or maybe some alarm or whatever it is. So, that is a case where UDP protocol may be quite suitable. This is used for some route updating protocols such as RIP. We have already discussed RIP. So, this for communication between the for updating the routes, the routers, if you remember, that they have to communicate with each other, and that uses UDP. So, these are just two examples. There are many other examples and user applications also which may use UDP. Now, let us talk a little bit more about port numbers, and then I will talk about client server today. So, port number. So, local host and remote host are defined by IP addresses. So, this is the host, mind you, that means the machine. A second identifier called port number is required to identify processes, because so many processes may be running on the same host. So, just identifying the host is not enough, you have to identify the process also, or more specifically you have to talk about this process in this host. Okay. So, you have to have a port number as well as an IP number. In TCP IP, port numbers are integers between 0 and 65,000. So, the server process requires a well known port number. The client process defines a port number chosen randomly by UDP, which is known as an ephemeral port number. Okay. So, we will discuss this in more detail very soon when we discuss more about client server. You see, this is one of the ways that computer, that means you write applications on a network, in a networked environment, by using the client server paradigm. So, there will be different servers giving you different services. For example, you may have a web server giving you web services, or mail server, and so many servers are there. And then there are clients who will be using that services. So, they use these port numbers, and they use different port numbers, different sets of port numbers. So, this will be clear when we talk about the client server paradigm in more detail. So, once again, if you think about the IP address, this selects a host, and then the port number, this selects a process. When you give this destination IP address something, say whatever, it reaches the particular sorry, particular host, and then in that host it looks at the port number and then selects that process which is using that particular port number. So, port numbers work as source and destination addresses for TCP or UDP segments. Ports ensure packets reach appropriate service on the server. The destination port field determines which service the source is requesting. TCP IP associates ports at the transport layer with certain applications. Now, software developers have agreed on well known ports. For example, a packet bound for an FTP server would use port 21. Okay. The point is, suppose just think of some network service, let us say think of say web service. Okay. Now, when you are browsing, that means surfing the net, that means you are using a browser, you may just click on a particular URL, or you may click on a particular address, a network address, and simply jump over there and you immediately get the opening page of that particular site on your that is displayed by your browser. Now, if you think about it, just how does it happen? A particular site is hosted in some remote machine somewhere, you do not even know where. You may know its IP address, that is all. Now, by knowing its IP address, you have to make a request to that IP address that okay, show me your opening page, let us say. I mean, I am just putting it very figuratively. Now, the IP address will help you, that means through this maze of routers who may be running some routing protocol like RIP or OSPF, so that your request reaches the destination machine. But in the destination machine, how does it know the port number? Because you do not know about the destination machine, you do not know how many processes are running, etc. So, how does your message actually request? I mean, suppose if it is a HTTP request, that means it is a request for a web page to a web server, then this request has to reach the web server. Now, there may be 10 other or 50 other processes running on that same machine. It should not go to any of these other servers. So, what is done is that for very standard applications like okay, let me name some standard applications like FTP, which is a file transfer protocol, SMTP, which is a simple mail transfer protocol, HTTP, which is a hypertext transfer protocol, and so on. So, these are all applications. So, for all these protocols, the port numbers are fixed. So, if I make an FTP request, as it says that FTP server will use a well known port 21, that means if I make an FTP request to any machine anywhere in the world, what I will do is that I am going to use port number 21, knowing that this is a so called well known port number, and this is going to, I mean, if it reaches the destination machine, it is going, the port number 21 would mean the FTP server. So, conversations that do not involve applications with well known ports are assigned ports randomly selected from a specific range. And we have that IANA, there is an organization which handles these port numbers. So, port numbers have the following assigned ranges. Below 255, that means 0 to 255, they are reserved for public applications like FTP, SMTP, HTTP, etc. From 255 to 1023, these are assigned to companies for marketable applications, and above 1023, these are unregulated, which means that from up to 1000, port number 1023, these are reserved, and that is also again divided into two parts. So, one part for the public applications and the other for some maybe vendor specific applications, but they are all well known port numbers. Now, think of the other direction. Apart from well known port numbers, you also need a whole lot of other port numbers. Say take the previous example that you have made an HTTP request to a web server. Now, the web server will send you back something, okay, will send you back with a reply, maybe it will be send you with the content of the opening the first page of its website, opening page of its website, that is going to be sent to the requester, but to which port? Now, for this another port number is temporarily assigned, and this is assigned from a number range from 1024 to that 65,000. All right. So, they say a number is randomly chosen. So, this is an ephemeral port, this is not a fixed port. So, for the duration of this communication, this port number is going to be held constant, and then it will be released for use by some other process. So, source port numbers are dynamically assigned by the originating host and are usually a number larger than 1023. Port numbers in the range of 0 to 1023 are controlled by IANA. So, these are some examples of some well known port numbers. These, I mean, there are quite a good number of them, but I have just mentioned some important protocols. For example, FTP, which is a file transfer protocol, this uses port number 21. Telnet, which is a terminal connection, which is a port number 23. By the way, I will be talking more about these some of these application layer protocols in a later lecture. Some of them, I mean, there are many I mean, nowadays there are hundreds of applications have come up. So, we cannot talk about all of them, but we will talk about a few of them. towards the last part of our course. So, for the time being, let me just mention them. Telnet is a terminal connection which uses the well known port number 23. SMTP, which is a simple mail transfer protocol, uses port number 25. TFTP, trivial file transfer, when you just have to send a short message, that uses 69. HTTP, which is the hypertext transfer protocols, which is the one is used for web services, that uses port number, well known port number 80. POP3, which is a post office protocol, uses the port number 110. What POP3 does is that, suppose you got some mail in your mailbox in the server, in the local mail server, then on your desktop you can download all the mails from the local server to your machine through the post office protocol. This is the POP3 protocol, uses 110 as the well known port number. 161 for SNMP. So, this is used for network management. There are a whole lot of others, I have just mentioned a few of them which are important. So, now moving on to the full description of a client server programming, we have it uses what is known as a socket address, and this socket is a combination of an IP address and a port number. This is called a socket address. This uniquely defines each client and server process. So, this process in this machine. So, this process given by the port number and this machine given by the IP number. So, these are some of the references for the different RFCs. The UDP is described in 768, RFC 768, and then there is RFC 1122. And IANA port number you can see in this particular site. Now, just a little bit more about the client server paradigm, which is sort of universally used for network based application. It's a server application is listener, waits for incoming message, performs service, returns result. Client application establishes connection. So, it sends a message to server, waits for return message. So, in this client server paradigm, usually what happens is that the client would initiate the request. So, it initiates the request for some service. So, it has to of course know the address of the service, and if it is a well known service, then it will use a well known port number. So, to that particular machine, in that port number it will make a request, and the server will accede to the request, in the sense that it will give the service and then go back, return the result to the client, and then go back to listening. So, the server is always in a listening mode, that means it is waiting for particular requests to come in. So, clients and servers exchange messages through the transport protocol, e.g. TCP or UDP. Both client and server must have the same protocol stack and interact with the transport layer. So, you may have a client server using both TCP and UDP. Protocols specify general operations, and the API specifies exactly how it is done. So, there is for using this socket, there is a socket API. API stands for application program interface. So, the socket API is the de facto standard. Origin is in the BSD Unix from University of California at Berkeley, as part of one of the first versions of TCP IP. Now, sockets, just a little bit about the socket library now. This is a vendor supplied library of procedures, have the same name and arguments as one of the socket functions. It promotes independent source code and usually easier to use than the original sockets. That so, the vendors also provide socket libraries with some bells and whistles actually. So, socket software interface designed to communicate between the user program and TCP/IP protocol stack. So, that is the internally that is a socket. Just think about it again. So, up to now all the TCP/IP stack that we have been talking about, right from the bottom one to right up to the transport layer, that is already in the system. Now, the point is you want to develop some application which you want it to run over the network. In that case, you have to naturally, so you will write your program for application program for doing whatever, giving whatever service you would like to give. Now, this application, this user program has to communicate with the this TCP/IP protocol stack, which is already in the machine, and the intervening layer is the API for sockets. So, you go to this TCP/IP stack through the sockets. So, socket is a data structure inside the program. Both client and server programs communicate via a pair of sockets. There are different socket domain families. So, there are significant socket domain families like internet domain sockets implemented via IP addresses and port numbers, Unix domain sockets implemented via file names. Then there are novel IPX, AppleTalk, etc., etc. So, all these other vendor specific socket domains are also there. So, the first two are the most important. And then there are two types of rather three types of sockets. Okay. One is a stream, so uses TCP protocol, it is a connection oriented service. So, a stream socket, this is a connection oriented circuit. Naturally UDP, I mean we have just discussed UDP, we have not discussed TCP as yet. So, naturally stream socket you cannot use with UDP. So, in that case the protocol, transport layer protocol to use is TCP. So, that is a stream socket. Then there are datagram sockets, SOC datagram uses UDP protocol. So, this is what type of socket it is determines that what type of protocol it is going to use, TCP or UDP. So, this uses the UDP protocol, and then there may be raw sockets which may be used for testing internally when you are testing it. So, for creating a socket you have to have a library, and for accessing the functions in the library which is that that socket specifically, you have to include that sys /types.h and sys /socket.h. I mean assuming that you are writing it say in C. So, you may have a function call something like this, int socket, int domain, int type, int protocol. So, when you give this socket call, you have to mention its domain, its type and its protocol. So, domain is one of the protocol families like PFINet, PFUnix, etc. So, that is the domain, we have socket domain families that we have talked about. The type defines the communication protocol semantics. Usually they defines either SOC stream, that means connection oriented stream, that is a TCP, or SOC dgram, that is a connectionless unreliable UDP. Protocol specifies a particular protocol, just set this to 0 to accept the default whatever. Now, I am afraid this is not very, this cannot be seen very well. So, I will just explain what is it, what happens in the client server. Actually, we have discussed only a part of it, that suppose that means that when the client is initiating a request, it has initiated a request, let us say for a standard kind of service. So, and it knows the destination IP address, it has given the IP address and the well known port number, this message has reached the destination machine. Now, in the destination machine, if you remember that a server program always listens to that particular well known port number. So, what is happening is that server program is actually in a loop. So, it is listening whether any request is coming in through that port number. Now, when it reaches in the case of a UDP server, this may be simple. So, it gets some request, it immediately gives a very short response and goes back to listening, that is quite alright. But in the case, in such cases where the interaction with the user may be prolonged, for example, the user may have made an FTP request, that means it is going to download a file. Now, downloading a file is going to take quite a bit of time. Similarly, it may have asked to download some, it may have made some HTTP request, that means it may have asked for a particular web page. Now, giving I mean putting that web page, sending that web page, that is also going to take a good bit of time. Of course, when I say a good bit of time, this is always in respect to the kind of speed that people are accustomed to. Now, think about this, if the communication is always through that well known port, then during the currency of this particular application, what is going to I mean this particular session between this particular client and the server, that well known port number is going to be blocked and other people will not be able to get the service. Now, that is not acceptable. So, usually in the client server what happens is that there is a handshake. So, a request comes to the well known port number, then and of course, there is a port address which has been sent by the client. So, the from the server side the response goes back with another ephemeral port number, which is not a standard port number. Now, on both sides you have two ephemeral port numbers, that means a port number which is greater than 1024 and they can then communicate through these two port numbers with source and destination respectively, depending on from which side it is being sent. So, these two different port numbers are used and this is on one side, this is happening. On the other side, this original server, it goes back to listening to that same well known port number, so that if a second request comes, it can again service it. Anyway, so these are the these things for a TCP server, although we have not discussed TCP as yet, but so far as this client server part is concerned, both of them are very similar. So, I thought I would discuss both of them here. So, sock init, it creates a socket, you register port with the system, you establish the client connection, you accept the client connection, then the read write of data, then the close is for shutting down. Okay. For that means in this part, when you establish client connection and when you accept the client connection, in this part all these two ephemeral port numbers, they are exchanged and the handshake takes place. So, this is the on the server side. On the client side, it creates a socket, then it tries to set up a connection. Remember that usually in a client server, the initiation of the connection is always from the client side, or almost usually from the client side. Then the write read goes on and then there is a shutdown. Similarly, for UDP clients and servers are similar, only thing is that it uses sock dgram instead of sock stream. So, connectionless clients and servers create a socket using sock dgram, and connectionless servers do not call listen or accept and usually do not call connect. That means, you may not require any specific handshake and you may not require a special ephemeral port for prolonged communication between the client and the server, because in this particular case the usually the service is just sending one message and then forget about it, that is over, the message the service is over. Since connectionless communications lack a sustained connection, several methods are available that allow you to specify a destination address with every call. That means send to, sock, buffer, and then there are a whole let me not go into the details of these parameters, you can always look them up in the manual. So, there is a way to specify a destination address with every call. So, for UDP server, the sequence of calls is the following: you create a socket, you register the port, that is the binding, we use the bind command, receive or send, and then shut down. So, this is a somewhat simpler than the TCP server, and then there is the UDP client which you create, you send or receive, and then you shut down. Now, there are two types of servers. So, several clients can request service of the server in the same time. In this case, a server can service one client at one time, other client requests must wait. This type of server is called non-concurrent, and the second type is that services of all client requests are handled simultaneously. This type of server is called concurrent. Now, this is what happens. In the I mean, just to elaborate on the server part a little bit more than what I have already discussed, the client request for a connection has come to the server. Now, what might happen is that the server, after all, what is a server? In this case, when I mention the term server, I mean that software process which is running there, not the hardware box. Our hardware box is also called a server in a different context. In our context, by server, I mean the process which is giving the service. So, this is some kind of process which is running in a particular machine. Now, what might happen is that in the non-concurrent case, what will happen is that all the user requests come and they are sort of queued up, they are sort of put in a queue, and what the server process, what it will do is that it will take out one from the queue, process the service and then give it back, and then send the result, then take the next one out of the queue. So, there is a queue where all the processes, that means all the client requests are waiting, and the server, that means the service process which is giving the service, this is taking one request at a time out of the queue. This is called a non-concurrent server. Non-concurrent in the sense that I mean, of course, when you are using an UDP kind of, you are using SOC DGRAM, that means UDP kind of service, that means it is a one-off kind of service, that means you get a request, send a message, and maybe that is the end of the service. In that case, this non-concurrent server or these are also called iterative servers. So, these iterative servers are more efficient, but it may also happen that in a particular service, the client server communication is for an extended period of time, in which case one particular request may block all other requests for a unnecessarily long time. So, what would in that case a concurrent server, the so called concurrent server may be preferred. So, in concurrent server, what happens is that the server, as soon as it gets a request at the well known port, it immediately spawns or forks a new process. Now, when you execute a fork in say Unix, what you get is a exactly similar or rather the exactly similar code, piece of code, which you make some changes. What you do is that you give them a new port number and let this new process communicate with this particular client's request, and the original process goes back to listening to the well known port. Another process, another request may come from some other client somewhere else. So, it will again spawn another process, and the original process will go back to listening to the well known port, and all these child processes, server processes which have been spawned, they all use different ephemeral port numbers to communicate with different clients. So, this is concurrent. Now, if you have only one particular processor in the server machine, let us say, you can only one program can run. So, in that way, in the strictest sense of the term, things cannot be concurrent, things have to be sequential, but then that sequentiality is imposed by the way processes are scheduled by the scheduler inside the OS. Okay. So, it will give you maybe some milliseconds for one process, then it give you another some milliseconds for some other process, etc. So, all the clients will get, so it will look as if all the clients are getting the service simultaneously. So, that is what we mean when we say that the client requests are serviced simultaneously. So, these are the non-concurrent server sequence of calls, we need not go into. So, only thing to note is that there is a loop over here, you see that while loop, start the loops, this loop will service each request sequentially, and then there is the concurrent server. So, which uses a fork, and in the fork it creates a child process which will now communicate with the client. Okay, with this we come to the end of this lecture. In the next lecture we will discuss the TCP protocol, which is slightly more involved. So, we will talk about it in the next lecture. Thank you.